Hey guys, we are going to talk about 3D rigid body equilibrium now. We already talked about 2D, now we're just going to add that third dimension. Now our equations, which we'll talk a little bit more about them in just a minute, are going to be basically the same, but since you're doing 3D, it's always a good idea with those moments to just use the vector version. So remember, for moments, if you're going to do a vector, it's r cross f. We're still going to be summing up all the moments, setting them equal to 0. But remember to use that vector formation. That tends to be a lot easier for students to see. And then we'll also sum up our force vectors, set those equal to 0. And we'll go into more detail about that in just a few minutes. First, let's talk about our support reactions. In the last section when we did 2D equilibrium, we had pins, rollers, rockers, we had a fixed support, we did normal force, and cables, things like that. So simple things that were only in 2 dimensions. Now that we've got 3 dimensions, we're going to add to that list. So the first one we're going to talk about is a ball and socket support. And what this is, it looks kind of like this. We've got basically a sphere right here. So think of a ball, and it's got this little arm attached to it. And what would go on here is this would be enclosed within some sort of spherical shell. Okay, and what that does is the socket will permit the ball to rotate around freely, but no translation is allowed. So if I were to think of this, if I were to draw a socket like this, so think about this being a sphere on the outside, and then you're putting this ball inside of it, and it's contained in that sphere. Since you have this arm, you could rotate this inside of this socket, but you couldn't translate it. You're not going to be able to pull it out. You can't go in the X direction or the Y direction. So you can't translate, but you can rotate. All right, so the socket permits the ball to rotate freely, but no translation. And if we try to translate that bar in any of the directions, we get a reactive force that prevents the rotation, or the translation, I mean, sorry about that. Now, the rotation is going to be permitted about all axes. So what that means for your free body diagram, when you do this, you're going to have 3 force components. So if I was to sit there and draw the free body diagram, let's say it looks like this. Then let's draw our coordinate system. Let's say this is X, this is Y, that's Z. The free body diagram on here, I'm going to have a force in the X direction, I'm going to have one in the Y direction, and then also in the Z direction. Okay? And these forces are what prevent the translation. The moment, or the rotation, is allowed because we don't have any couple moments provided by this support. And the easiest example to think of for this is think of your own hip joints. Those are ball and socket joints. All right, so your hip can rotate about that joint, but it can't translate. All right, you can't pull your, or at least we hope, you can't pull your leg away from your body, right? So human hip joint is an example of a ball and socket joint. So just remember, no translation, but it does allow rotation about all 3 axes. A roller, we talked about rollers before with the 2D system. Same thing for this one, for 3D. So if we were to draw the free body diagram, let's draw our coordinate system. Let's say that's X, Y, Z. If I were to put a mass up here, this roller, all it does is it supports this mass. All right, the mass is just sitting on that roller. So essentially the roller just provides an upward force. All right, so that would be FZ. And an example of that, you have wheels supporting furniture legs. If you've ever seen those old-timey tables and they've got the wheels on the bottom of the legs, those could be rollers. Or the rollers on the chair that you may be sitting on. All right. So they're just supports. A mass can rest on the roller. Now, let's talk about a hinge. Everybody has seen a hinge. Now, a hinge, if you think about what happens when you open a door, the door rotates about the hinge axis. And the hinge axis is the one that goes through the center of the hinge. So if this is our hinge, an axis coming through here would be the hinge axis. All right, and we can rotate about that axis, but we can't rotate about any of the other ones. All right. So if we were, I'm just going to do it on here. Let's draw our coordinate system. And let's call that y. So if you think about it, when you have your door, if we were to draw the forces for our hinge support, can you translate the door? Can you like displace the door? Can the door move away from the door frame, assuming the hinge is put on correctly? No, right? So no translation in any direction. It's not going to move to the left or the right or up or down, anything like that. So we've got forces in each of the directions. Those are your reaction forces. They prevent the translation. And then the only rotation you get is going to be about this hinge axis, right? Because we can rotate this way, but we can't rotate this way, right? Can't do that. You can't rotate about this axis either. So the only axis you can rotate about is this hinge axis. So keeping that in mind, that means we're going to have couple moments produced about the other two axes. And those will prevent the rotation about those axes. So let's just call this MAZ, and then let's call this MAX. So these two prevent the rotation about the other axes. These forces prevent the translation. Okay. So remember, no translation in any direction. So for that, we have the reaction forces. And we can only rotate about the hinge axis. All right, so to allow that, we're going to produce these two other couple moments that prevent the rotation about the non-hinge axes. All right, so that is a hinge. Now let's look at a thrust bearing. And here's just an example of a thrust bearing. What this is we've got a circular shaft that comes in here, and this circular shaft, we want this to be able to rotate about this axis. All right, so we want it to be able to spin around this axis and rotate. We do not, however, want it to translate in any of the directions. All right, so since we don't want it to translate in any of the directions, let's draw out our coordinate system here. Then if that's x, y, and then let's call it z, then what we get is we get our three forces. Those are going to prevent the translation. So it's going to keep this shaft in place so that it doesn't get displaced. And we only want rotation about this one axis. So to prevent any rotation about this z or x axis, we're going to produce couple moments. So I'll just call that one MAZ, and we'll call this one MAX. There is no moment produced about the y-axis because we want to allow for that rotation. All right, so you got these two couple moments and then your three forces. And that's a thrust bearing. Now there's also something called a journal bearing. The journal bearing, if you see that, it's essentially the same thing, but a journal bearing will allow this shaft to move back and forth along this axis. So it would not produce this force here. All right, so when you see your problem, you have to figure out what kind of bearing you've got. And just remember, a thrust bearing is producing this force to keep this fixed in place. A journal bearing will allow this to move back and forth. All right. And if you look, these reactions are basically what we had here with the hinge axis, or with the hinge support. And next one, let's look at the fixed support. This will be our last one. There are other ones, but these are the main ones that we'll talk about. The fixed support, we've talked about that before. In the previous 2D examples, we talked about a welded support. So basically it fixes the object in place so that it can have no motion of any kind at all. We're not going to have any translation at all, and we're not going to have any rotation. The example I put here is we have a concrete pillar that's holding up a bridge. So now for the free body diagram, if you were to draw that out, let's say this is our concrete pillar here, for example. Now think about what's going on here. We have a fixed support. We don't want this thing to move at all, right? So that means our fixed support is going to have to provide a force in each direction. So we've had our Fz, our Fx, and the Fy. And now we don't want any rotation either. So the support has to counteract any sort of rotation that's produced by the pillar. All right, so we're going to have a moment here about the x-axis. We'll have one about the y-axis, and then put it up here. We've got one about the z-axis. Now, when you do these problems, you shouldn't have to have these memorized. Okay, you should be able to think about what the object is doing, what the body is doing, and figure out what forces and moments should go on these supports. Just remember, forces are provided by the supports if they're preventing translation in a direction. The couples are provided by the supports if you're trying to prevent rotation. So those are the key things you need to remember. So try not to just memorize these things, because then you're not getting a full understanding of what is happening in the problem. All right, a couple more things I want to talk about. We talked about some of these supports having moments being produced. So we had the hinge, it produced moments. The bearing supports produce moments. And then we didn't talk about it, but a pin in a 3D system can also produce moments, because if you think about it, it's only going to allow the rotation about the one axis. So moments would technically be produced with a pin also in the 3D system. Now, if you think about these being used together, so if we've got 3 hinges holding a door up, do we really need the moments produced by the supports when it's already got the 3 hinges? So think about if we have a hinge here, here, and here holding the door up. Since these are fixed in these 3 places, is that door going to be able to rotate about any of the other axes other than the hinge axis anyways? No. All right, so it can't rotate about the other axes anyways. So because of that, we can say it's properly aligned, which is what we have got underlined right here. And when we say it's properly aligned, that basically just tells you you only need to look at the force reactions. And that's just because the supports all work together to prevent any sort of rotation. All right, so that's what it means if you see properly aligned. If you see that, you just look at the force reactions. You don't need to look at the moments produced. Okay? Now, let's go over our equilibrium equations. I said we'd talk about these again. So remember, we're going to have the sum of the forces equals 0. And then the sum of the moments equals 0. And again, you're going to pick a reference point that's easy to use. These are moment equations. So how many equations do we get for each one of these? We get 3 for each of them. All right. So from the force one, we get the sum of the forces in the x direction is 0. Sum of the forces in the y direction is 0. Sum of the forces in the z direction, 0. And now for the moment equation. When you do the vector formation of the moments, you get the moment about each of the axes. So you're going to get your sum of the moments about the x-axis, that'll be 0. Sum of the moment about the y-axis is 0. Finally, some of the moments about the z-axis will be 0. That gives you a total of 6 equations that you can go through and solve. All right, so how many unknowns could you have if you've got 6 equations? You could have 6 unknowns. So let's put 6 equations, means we can have 6 unknowns. All right. So these problems are going to be longer than in the 2D problems. The 2D problems, we only had 3 equations. Here we've got 6. So more algebra for you. I know you're excited. Now before we get to the examples, 3 more definitions we need to cover. Statically indeterminate. If you hear statically indeterminate, what that means is your structure is going to possess more external supports or constraints than what you need for equilibrium. Basically, you could remove some of those supports and you'd still have equilibrium. That's what statically indeterminate means. If you were to go through and solve your system and try to find all the unknowns, you're going to have more unknowns than you have equations. Right? And that's because you have more supports than what you need. Okay, so you won't be able to solve this kind of problem because you got too many unknowns. Redundant supports, those are going to be supports where you can remove them without changing your equilibrium, right? So you're just kind of overdoing it. And then statically determinate, this is what we kind of hope for. These are bodies that are supported by the minimum number of constraints needed for equilibrium. All right, so here you'll have the right number of unknowns with the right number of equations. Okay, so I just wanted to cover those terms in case you hear them. That's just a few terms that are sometimes used. All right, guys, I will see y'all in the next video and we'll start the examples.